In this video, I'm going to talk you through how to do all the mechanics questions that were on the AS Paper 2 Stats and Mechanics paper, the specimen paper. Okay, so for each question, I will start off with the question just being blank, so you can pause and have a go with no help. We'll then move on to, I'll just give you a bit of a hint. So if you're not quite sure where to start, I'll just sort of set you in the right direction. And then finally, for each question, we'll then move on to a sort of a work solution. Right, so the first question on part B on this paper was question 5. So this is the question if you just want to pause and have a go without any help. All you've got here is are the Suvat equations straight out of the formula booklet. So the hint for this question, I've just done a little sketch down here in the corner. So we start off 19.6 meters up. We then project the ball upwards and it takes 4 seconds for it to hit the ground. So what do we know? Well, I think it's always wise to resolve in the direction of the initial motion, which is upwards. So our displacement is minus 19.6, is that's below us. The time taken is 4 seconds, and the acceleration is gravity, which is obviously downwards, so that's minus 9.8, and we need to work out our final velocity, so v. So use the appropriate Suvat equation to find v when you know S, T, and A. Now for part B, we're resolving upwards. Okay, so we're using the model to find the height of B above the ground. The key thing is at the maximum height, the final velocity is 0. Okay, so when it comes to the instantaneous rest at the point above B, its maximum height, that is when the velocity is 0. So what do we know here? We know that our initial speed was 14.7. We know that the velocity is 0. We're fighting against gravity. A is minus 9.8, and we're trying to work out the displacement. Okay, so choose the appropriate Suvat equation to find S when you know U, V, and A. So the answer for question 5 follows now. So we had the sketch and the initial starting point for Suvat in the hint. So on this occasion, we're using that quite rare Suvat equation, the third one down in the formula booklet. So we're using S equals Vt minus a half At squared. Substituting into that, we can work out that V is 24.5 meters per second. That's the speed, okay? We calculated that the velocity was minus 24.5. Now, velocity is a vector, that's got direction, but as the question asks for the speed, make sure you just give it as 24.5, okay? Speed is always positive. Now for part B, so after the ball's hit the ground and it goes upwards, and we're trying to find the distance when it comes to rest. So we've got U is 14.7, V is 0, A is minus 9.8, and we're trying to work out the distance. So substitute into V squared equals U squared plus 2AS, and we can work out that the distance is 11.0 meters. Now for part C, how would this new value of the speed of the ball as it hits the ground for the first time compare with the value found using the initial model of part A? This is when we're adding in the air resistance. Well, it's obviously going to slow things down, so the new value for speed would be lower. Question 6. So I think really the only hint I can give you here is just that it's a triangular shape, and you've just got to work out what value to put here on the x-axis and up here on the y-axis. Now for part B, remember that the area under a velocity time graph represents the distance travelled, which we're told is 1,500 meters. So use the area of a triangle, half times base times height equals 1,500 meters to work out what V is. So the solution for question 6, so it's an upside down V shape. It takes 120 seconds and we're told that it's capital V is when it's finished accelerating. So for part B, to work out V, well, we know the area under the graph represents the distance. So half times base times height. So half times 120 times V equals 1500, and solve to get V being 25. Now part C, it is given that the car accelerates uniformly for t seconds. Explain why there is a range of possible values for t which satisfies the requirement of the model. Okay, well the point is that this point can just flex across. Okay, t can just be anywhere, and we still get the area under the graph being 1,500. So it's not dependent on t. All right, we can move this point here anywhere along here, and the graph will just still give us a half times base times height equals 1,500, because the distance travelled does not depend on t. Now for part D, suggest one improvement to be made to the model that will make it more realistic. Well, they've suggested we just include a constant speed phase in the motion. So rather than just accelerating, then instantaneously we decelerate, we just have a little period of time where it just plateaus at the top and it's flat. Question 7. So for the hint, I'm just going to complete the diagram for you. So remember, you have the tension arrows pointing towards the pulley. We've got the resistance to the motion of 1.5 newtons up here, and we've got the weight of Q being mg. Now for part A, to work out the tension in the rope, we're going to resolve for P. And we're doing that because we can't resolve for Q because we don't know the mass. So we're going to resolve for P in the direction of motion, which is left to right. And again, always start these off. Just write down F equals ma to gather your thoughts. So on the left-hand side, you're going to have to net off the forces. So you've got forces of the tension and the 1.5. Now get it the right way around. Is it T minus 1.5 or 1.5 minus T? Which is the greater force, given that we're traveling left to right? Now for part 2, in order to find the value of m, so the mass of Q, we're going to resolve for Q again in the direction of motion, which is going downwards. So the same thing, resolving downwards. So the two forces involved are going to be the weight, which is mg, and the tension, which is going to be greater given that it's moving downwards. So is it going to be mg minus t or t minus mg? And then if you then go and substitute in knowing what T is, and you know the tension from part A, you're then able to work out the value of M. Now for part B, the time after release for Q to hit the ground. Well, what do we know for Q? We know the acceleration, we know that U is 0. We know so initial speed is 0. We know the distance we're traveling is 2 meters. We're told that the acceleration is 2.5. We need to work out what the tension is. So use the appropriate Suvat equation when you know U, S, and A, but you're trying to work out what T is. So the solution for question 7. So for part A1, we're going to, from the point of view, well, we're resolving for P in the direction of motion, which is to the right. F equals ma, so our net force is the tension minus the 1.5 resistance. So that's our net force. The mass is 0.4 and the acceleration is 2.5, allowing us to find the tension of 2.5. Now for part 2, to work out m, the mass of Q, we're going to resolve for Q in the direction of motion, which is downwards. Our net force is mg minus t. Make sure you get that the right way round. We're going downwards, so the force downwards must be greater than the force upwards, otherwise we will be going upwards. So mg minus t equals is the net force, and that equals the mass times the acceleration. We're told to use G being 10 in this question. We know the tension is 2.5 from part A in the question, so that allows us to work out that M is 0.33 kilograms. Now for part B, we're going to be again resolving for Q. Again, always I think we do in the direction of motion, so resolve downwards. It's initially at rest, so our U is 0. The distance it travels before it hits the ground is 2. The acceleration is 2.5. We need to work out what T is. So using S equals UT plus half AT squared, we can work out that T was 1.3. Now for part C, state one limitation of the model which will affect your accuracy. Well, they suggest we can either use the mass of the rope, or the pulley may not be smooth, or you could say air resistance. Any of those would suffice. Question 8. So we're given the velocity equation. Now for part A, we've got to work out the distance travelled. Now how do we move from a velocity equation to the distance equation? We have to integrate. So make sure you integrate this, and then it's in the first second, so just substitute in when t equals 1. Now for part B, the value of t at the instant when p changes its direction of motion. Well, it changes direction of motion when it comes instantaneously to rest, which is when the velocity equals 0. So set this equal to 0 and solve for t. Now for part C, the value of t at the instant when p returns to its starting point. Well, it returns to its starting point when the displacement is 0. So take your displacement equation from part A, set that equal to 0 and solve for t. So the solution to question 8. Now for part A, we want to work out the distance travelled by p in the first second. So we need a displacement equation. To get that, we integrate the velocity equation. So we integrate 16 minus 3t squared, and that gives us 16t minus t cubed plus c. Now we're told when t is 0, the distance travelled is 0. So substituting in, we can see that c was 0. So s equals 16t minus t cubed. So substituting in when t is 1, we get the distance travelled being 15 meters. So part B, the value of t at the instant when p changes its direction. Well, this is when velocity equals 0. It changes direction, or when the velocity is instantaneously 0. They are the same thing. That is when the velocity equals 0. So 16 minus 3t squared has got to equal 0. So solving for that, we get t being 2.3 seconds. Now for part C, we return to the starting point when the displacement is 0. So we'll take a displacement equation from part A, 16t minus t cubed, set that equal to 0, factorise, and we get the solutions of 0 and 4. So obviously 0 is when it's initially when it starts its journey, and it returns to its starting point when t equals 4 seconds.